Good afternoon, everyone. So welcome to the MIT Robotics Seminar. It's an absolute pleasure and honor to have with us Mark Cutkosky, who is visiting us from Stanford, where he's a Fletcher Jones Professor in the Department of Mechanical Engineering. Mark was at CMU until 1985, where he did his PhD, and he also worked as a design engineer at Alcoa in Pittsburgh. Right, so Mark has been doing a lot of very good work in manipulation and tactile sensing, and has had amazing students graduate from his lab, such as Rob Wood at Harvard, Sangbei and Maria at MIT.
Yes.
So, very excited to have you, Mark, and looking forward to your talk. So please take it away.
Thank you very much. Hey, everybody, it's great to see you here. And Pulkit didn't kind of tell you the backstory. It's at least partly his fault I'm here, because we invited him to come to Stanford, and I was introducing the famous speaker Pulkit. And of course, then when somebody comes all the way to Stanford and they say, by the way, have you been to MIT lately? It's hard to say no. And so, yeah, I mean, it's actually great. I haven't been here since before COVID, and it's really great to see the energy and the new facilities for the robotics labs, and it's been really very exciting to talk to I really wish I could bring you all to Stanford. The weather would be, actually better. Okay, so for those who know me, and quite a few of you do, I'm kind of like the bio-inspired robot guy, and I'm sure the last time I was here, I brought, maybe the StickyBot robot and gecko adhesives. I'm not going to talk about that today. I'm going to talk about a project we have with Marco Pavoni and AeroAstro, and with NASA. And on the face of it, not bio-inspired at all. The idea is to have a robot, a small robot with very long arms that can explore caves and lava tubes and structures like that on Mars or the moon. And if you would ask yourself, well, could bio-inspiration be useful? Why? I mean, there's the environment on Mars is so different from anything on Earth that it doesn't really make sense that any biological exemplars would give you important insights. And yet, I am the bio-inspired guy, and so I can't help thinking about it. And so even if it's reverse bio-inspiration, I'm going to work some in. Okay, so as I said, the motivation here is to explore these really very difficult spaces. This is an actual lava tube. For those who don't know, a lava tube is, you have a volcano, it erupts, the lava flows down. As it starts to cool, the top surface solidifies, but underneath there are channels that keep flowing. And eventually they empty as the eruption stops, and you have what looks almost like a subway tunnel underground, long, thin tunnel, and periodically there will be openings where the ceiling has fallen through. It is, these are interesting to explore. It is hypothesized that if people would eventually set up habitable spaces on the moon or Mars, these might be very good spaces to try to do it. You're protected from a good bit of radiation. It has a more stable thermal environment. You could seal off a chamber. It might be a place to do it. Also on Mars, the thinking is that if there would be any signs of previous life, this might be a good place to live or to look for. And that is why one of the members of our team, who I didn't introduce but should have, is Mathieu Lepotre. He's a geophysics professor at Stanford and is very interested in studying caves and lava tubes. And then through the talk, I'll be showing slides from Tony and Julia and Stanley and Dan, who are the students who really do all the work, of course. So how will we get about in these spaces? Flying robots and ingenuity, hats off, it's wonderful. It's amazing what that flying robot could do on Mars. I think it vastly exceeded everybody's expectations, but it is a hard thing to try to run inside a lava tube. And of course, on the moon, it won't work at all. So what else might work? So the canonical solution, and it's interesting, I had dinner last night with Aaron Parness, who was one of the developers of the Lemur robots from JPL. Again, they're very impressive. They use microspines to cling on to surfaces. And this is a complicated robot, but it's also not very big, and therefore it can't move very far with one step. It has to it does a tripedal crawl. It keeps 3 legs on the surface at all times for safety, and then moves 1 leg at a time. And the workspace, the reach space of possible grasping sites is just not that large. So it moves very slowly. Large obstacles are big things to clamber over or try to get around. And it's always a little bit precarious. So the thought was, what if you could have something that has sort of the compact form factor of a lemur, but can reach a really long way? And that was the idea behind ReachBot. So I have a little GIF here, which was prepared by Stephanie Schneider for her PhD defense, and I love it because it in a moment kind of captures the idea behind ReachBot. So they were doing some science, drilling into the strata. I think it concludes with taking a selfie. Yeah, but no, important optical sensing of the lava tube floor, right? All right, and if you want to see this, if you want this GIF or other stuff for ReachBot, just go to BDML Stanford ReachBot. Well, you know, the idea of having a small body with really long limbs, okay, here comes the retroactive bioinspiration part. Small body with really long limbs, I mean, it's a good idea. It's been around for millions of years. These are harvestmen. They're not spiders, they're arthropods, but they have a small body, very long limbs, and this gives it the ability to navigate in very complex three-dimensional terrain. But you may also have recognized that there's potentially a scaling problem here. The largest Spidermen are, you know, maybe about that big. You don't see any the size of a dog, or where the body would, let's say, be the size of a suitcase, and the limbs could be 20 or 30 feet long. And it's probably for us just as well, unless you like the spiders in Lord of the Rings, the cave spiders. So yeah, the problem, of course, is that mass goes as length cubed, beam strength goes as length squared. We're prone to buckling, and in fact, what you see these spider harvestmen do is in very windy, stormy weather, they'll stretch out sprawled and load their legs mostly in tension because they're stronger that way. And that's a good trick. Still, scaling's an issue. However, you might ask yourself, how big could this form factor get? Like if gravity was really not so much of a problem, and if I could start using stronger materials. Are there any spider-like morphologies that go to several meters, maybe 10 meters in diameter? Yeah, if gravity's not a problem, the morphology can be successful. So there we go. All right, so that's part of the idea behind ReachBot. The other part is an enabling technology. These are space booms. They're used for antennae in space or other space structures. They're carbon fiber, they're deployable, and they're quite strong. And if you think about it, it's a nice solution, because what if you, unlike the harvestman spider with jointed legs, what if you said, well, what's the simplest possible structure I could have that would give me a really long leg? Well, you know, there's some appeal. Except for buckling, right? So if I make it out of a stronger material, I may be able to go pretty far, but I'll still have something which is probably stronger in tension than it is in compression or bending, but that's okay. The other thing, so the second principle, the first principle is this idea of a small body with really long limbs, and in this case, we're using these deployable, unrolling space boom type structures. The second is that we want, at the terminal ends, we want something that can grip and grip strongly. So here we're going back to the same kind of idea as in lemur, where we've got grippers with microspines, and we can pull actually with tens or even 100 newtons. And this is not entirely a new idea either. If you can have several limbs and you don't distinguish too much what's an arm or a leg, and you have strong grasps at each terminal end, what's interesting is that in a difficult three-dimensional environment, this means that locomotion becomes manipulation, where you manipulate yourself. And that's interesting, because that means that there's a whole big body of grasp theory which is, can be adapted to our purposes. And I've been working on hands and grasping for 30 years, I guess. And the basic idea is you have several coordinated fingers. They're pressing upon a body. You want to express what happens in terms of what the grasped object should do. The fingers have constraints and due to friction, and the fingers can push, but they can't pull. We have the opposite problem. To a first approximation, we have very long beams that can pull but not push. Well, they can push a little bit, especially if they're not too long, but to a first approximation, instead of fingers that push, we have beams that pull. And the one part that's a little different, really, is the details of the contact. Instead of talking about friction cones and whether the finger can push without slipping and therefore the force vector has to be inside the friction cone, we now talk about we have a spiny gripper. The gripper has some sort of limit surface of applicable forces and moments, and we're going to try to make sure that all the grasp forces stay inside all their limit forces, limit surfaces, and that's what I'll be talking about more in the next few slides. So kinematically, each arm is a 6-axis chain. We have a 2-axis pan-tilt shoulder. We have a very long prismatic axis for the arm, and then we have a passive wrist. We're looking also, could you have an active wrist? Maybe, but we're really trying to minimize weight at the end of these booms, because when you have something, just like you saw with the tape measure here, when you have something that's going way out, you really would like what's out at the tip there to be as light as possible so that you can steer it to a likely grasp point. And of course, our first prototypes were in fact these, mounted on a platform. All right, so spines. We've done a lot of work over the years in spines. Many of our students at JPL and elsewhere have been looking at spines. And the gist of it is that at the microscale, it's still friction. So what happens is you've got a rough surface, and you've got a spine interacting with the surface, and depending upon the details of the contour right at that point, that will determine in which directions I can exert force and not have it slip and not have it pop off, okay? And then for a collection of spines, I can talk about what's the probability collectively that some aggregate set of spines will be able to exert a certain force and not slip and not pop off. And so in the end, what we get is a kind of a probabilistic estimate for how much force an array of spines should be able to exert depending on the roughness of the surface and depending upon the contour, the geometry of the surface. And that is the beginning to our grasp force analysis. So here I'm talking about grasping at the level of one gripper that's at the end of one of these very long arms, okay? So we have a stochastic distribution of spine contact angles. This depends on how rough the rock is, how sharp the spines are. We like to use two things that we like that work really well. One of them is suture needles. The other is Japanese microfishing hooks. And I think it's wonderful that Japan, the country that developed bonsai, also has a hobby of microfishing. And the fish hooks are really good, and we buy a lot of them. And we put them in our grippers. All right, so you do grasp analysis. We want to maintain force equilibrium. We also have some geometric constraints. We want not to have any fingers pop off the surface when we apply loads. And we want to have load sharing, meaning that when I apply a force to the whole gripper, there should be forces shared among all three of the fingers. And what that means is that I can now say, under these conditions, I can do a grasp analysis, and I can say, for a given force and moment, should this grasp be able to satisfy it? And the answer is stochastic. So there will be an expectation, and there will be a fairly big variation, because spine surface contact is inherently probabilistic. I can tell you what the estimated force is, but it's just like the probability of rain tomorrow. There's variation associated with it, and that's something to keep in mind as I continue to go along. So we get our estimated pull force. And we then do a Monte Carlo simulation to build up a limit surface. So given a set of possible pull forces, and given what we know about the geometry of the surface that we're grasping, and given what we know about how rough it is and how many spines we have, we can do this predicted limit surface. And the results look like this. And I thought I would just point out one thing, which is kind of interesting. So here we have a spine, an area where a spine is interacting with a bump on the surface. And what's kind of interesting is that if you have a gripper holding on a surface, what this plot just shows, it's the ratio of, pull force on the gripper to internal grasp force. So if I'm grasping this bottle with a certain internal force, and you ask me, how hard can you pull it? Here, go ahead, we'll try it. You pull it out of my grasp. That's exactly the ratio we're plotting here, okay? So it's pull to internal force, and as a function of grasping harder. And you can see that it really depends a lot on these angles, which again depend partly on how much I'm wrapping around like a surface on the rock and how rough it is. And so what this tells you is that unlike all of our previous work where we had robots climbing more or less flat cement or cinder block walls, there really is a big advantage if we scan the surface and say, aha, there is a little knob-like protrusion. Let's go there. Because it means that I can do like the yellow or purple line and not the blue or the orange line. It makes a big difference. So we're now, in contrast to before, like with Lemur, like with SpinyBot and all, we're now taking advantage of our very long reach to look for things that look like they might be good to hold on to. And we can do that because we have a large workspace. Before I move on with other stuff, any questions on any of that?
So can you determine that it's actually a usable spot?
Good. So I'm going to talk a little more about this in a couple of slides coming up. But what it comes down to is a kind of a two-stage sensing thing. And Julia D is the main student working on it. So with a camera at the body of the robot and lighting, I can get an idea that, there looks like sort of a bumpy thing that I should go. And then I have another small RealSense type camera out on the limb that as I get, less than a meter, I can look at it in more detail, see really what the roughness is. And that says, yeah, you should go like that and grab, or nah, we should retract and go elsewhere. And there's an interesting point, I'll probably get into this again later, but there's an interesting kind of point there, which is that there's a fairly high level of commitment. And I'll touch on this later. It's not as much as like when you're flying a drone and you try to perch on a tree, and you've made a big commitment at that point, because if you fail, you have to do a very quick recovery and not fall to the ground. Here, if we fail, well, we have to basically retract and re-aim and go again, because my ability to steer when I'm all the way out there is not very good. So it's not like a robot on a tabletop where if you have vision and you're looking and you have a failed grasp. If you have failed grasp, so what? Just try again. Now it matters a bit, but yeah. All right, so here is the results of the limit surface. And again, I just wanted to sort of point out a couple of interesting things. So we get a plot of what we think the maximum pull force could be in X, Y, and Z. And these are all our Monte Carlo points. It's a kind of a closed, convex polyhedron in force space. I have a ball joint at the wrist. So if I put my coordinate system there, I don't need to worry about moments, so I can plot it in a 3D space. And what you see, first of all, is not surprisingly, if I'm willing to grasp harder, then my maximum full force increases kind of linearly. If I have more spines, things improve, but you can see I start to hit diminishing returns, right? So 20 spines is noticeably better than 10, but 50 spines is hardly any better than 40. And one more thing, you notice that they have a kind of a flat surface here and here. That's due to that constraint about not having any fingers like pop off the surface when you load it. So that causes like a facet. And does anybody have any ideas? Like why would it be that, 20 spines is really a lot better than 10, but 50 is not that much better than 40? What do you get?
Overcrowded? Do they like get in each other's way?
They don't get in each other's way, but you're close.
Conforming to the surface?
You might not get perfect conformation. So yes, depending on, and this was a lot of Tony Chen's work, and I'll show the gripper later, is how well can we actually conform to surfaces. That's part of it, but there's even a more fundamental reason. This is the work of Xishuan. I was talking to one of the students who knows him from Flexiv, and Hao Zhang. There's a sort of a fundamental spine problem, which is load sharing. The problem is, if you have one spine, it can only exert a little bit of force, maybe a Newton at best. Well, okay, if I have 5 spines, I should be able to do 5 Newtons. Well, no, first of all, because of this stochastic thing, but secondly, that assumes that I can take my total force and distribute it perfectly evenly among the 5 spines, which means I need a suspension system, which we do have, but no suspension system is perfect. And so to the extent that we do not get perfect load sharing, that's why you start to see these diminishing returns. That it improves rapidly. I see Matt nodding sagely because he remembers us going through this stuff with SpinyBot and Boston Dynamics. It improves rapidly, and then it's like, okay, no more spines. Yeah. All right, so here's Tony's gripper. He worked endlessly on this. It's an amazing piece of under-actuation. Remember, we're trying to really minimize weight at the end of these long booms. So it's all one rather small motor, heavily geared down. There are tendons for actuating, and then there's a tendon for release. Many degrees of freedom. We actually did a study, how many degrees of freedom do we really need along each finger, and where do they need to be, and found a combination that seemed to work best over these kind of protruding surfaces. How many phalanges do we really need? Where do the joints really need to be? And I wouldn't say it was a formal optimization, but this combination really did seem to work best. And if we take out 1 degree of freedom, it works noticeably less well in terms of how well it conforms to the surface. And here we're using what are called spine tile arrays. This was actually the development of Hao Zhang, now at Flexiv. We found that this dense packing of spines, where each one of them is on a spring-loaded linear little, they're in a sleeve, in a hole. So they're actually very soft. I should have brought one in. If you touch it with your finger, it's so soft that it doesn't hurt. It's not perfect load sharing, but it kind of more than makes up for it in spine density. So there's our spine array, and there's our gripper, and that's it actually matched quite well with the limit surfaces that we had. So that's about as much as I wanted to say about gripping. Let's talk a little more about some of the other parts of ReachBot. Another very important part is motion planning. So this is the work mainly of Marco Pavoni's students. Given some knowledge of the environment in which you find yourself and a set of possible grasp sites, you decompose the motion planning into 2 parts. First, we choose a grasp that will be stable and will allow us to resist disturbances, and then we move the body while keeping the arms in place until we get to the end of our range of motion, at which point we detach a boom and put it somewhere else, and we continue. So that's the process. And Stephanie was the main person to do this motion planning, and there's now a new student, Dan Morton, who's taking over this work. So there you see this kind of slow motion. Actually, one of the nice things about space robots is that people do not mind if they are slow. Would not work for manufacturing. So people have asked, are we doing dynamics in our motion planning? Well, no. The only time we have to worry about dynamics is if a gripper loses its grip suddenly, and they will do that sometimes because it is stochastic, no matter how well you predict things. Even the rock could fail. You're gripping on a piece of rock and it just fractures. That sends a kind of a shock wave in through the system, and so we need to pick stances that are robust with respect to that, and that's part of what Stephanie's work is about. Okay, and then somebody was asking about do we look for sites? Yes, so this is Julia's work, and as I mentioned, it's a two-stage thing. So we look from the body to find what we think might be a good site, and then as we get close, we build this more detailed map of surface texture and geometry, looking for places that we think will give us a high ratio of pull force to grasp force. And as you get closer, you can actually look at the surface in fairly good detail. So this is a real scan from a lava tube in the Mojave Desert. And that's a good promising looking feature. Last May, Tony and Julia and Stephanie went on a field trip to the Mojave Desert, where they have very many lava tubes. It was kind of outside scope of our project to build a full-on ReachBot, but we could build one arm and mount it on a heavy surveyor's tripod. And so, I'll let it run here as it finds a site and pulls. And then we're interested to see whether the actual maximum force that we can exert matches our predictions based on what we know about the rock. And this stuff is coming out in a paper in Science Robotics soon, like any day now, I hope. And this is the point I mentioned. Yeah, so some of our findings of these field experiments are, as I mentioned, targeting with ReachBot does involve a level of commitment. You really want to sort of know that you're going in a good direction before sending a boom out there. We found the need to do near and far scanning, and the third point is what we were talking about with robustness. You want to, at all times, be choosing stances that are robust with respect to disturbances. Yeah, question, please.
Sorry if this was touched upon earlier, but why is it a high commitment? Like, other than
Yeah, because unlike a robot, doing bin picking or grabbing things on a table where I grab, and if it drops or it fails, I mean, it's no big deal. I'll go grab again and again. Here, by the time I've sent something out 20 feet, first of all, it takes time to do that. But secondly, once I'm out there, my ability to steer and reposition is not at all good. It's kind of like that tape measure. I mean, it's better because it's a carbon fiber boom, but it's still not very good. And, small error at my shoulder is a big error out at the tip. So I kind of want to be, in fact, what we usually have to do is retract and try again. So yeah, it's a time commitment, but it's still a commitment. Yeah, good question though, thanks. Yeah.
Kind of direct follow on, have you played with plans that retract partially and rotate and then...
No, and we should. I think it's an obvious thing to do. Moreover, there's this issue on boom and how long the booms can really be without buckling, and with also that as you roll them up, how big do they get, in the rolled up state? If you're really going to be in a cave or a lava tube, is there any reason why your booms ever need to be less than a meter long? Maybe not. So maybe that's the minimum distance, and then you go outward from there. Whereas right now, we can suck them all the way in, which I don't think is necessary unless you try to go through a very narrow passage or something. But yeah, it's a good point. Yeah.
So while choosing the grasping site, are you always trying to find some bumps, or can you
bumps
also
could either be two or doubly or singly curved. So if it's a sort of a bump-like thing that's doubly curved, or you can find things that are kind of like a ledge
Okay.
Yeah.
So, but
And-
why you are not choosing something like which is a hole, and then we put that, and then trying to?
You could, but I
grasp
think
it like
I
that?
bet that if you and I actually go through the analysis, we can prove to ourselves that I can get a stronger net force on the bump. And it's mainly intuition at this point, but I think the math will show it. And here's why. You know how there are like these lifting tongs that are used for construction equipment, where it's a kind like ice tongs sometimes, but lifting tongs for lifting blocks, and they don't need any internal force at all. You know, just the weight causes the grass force. Yeah, I think just pulling, it's easier to make just that pull force increase the internal grass force. If I go from the inside and go out, then it's like rock climbers who use like one of those wedge jamming things. I have a feeling that I have to push harder. Nonetheless, you know, that could be a solution. I mean, there's nothing to say that you couldn't have a wedge tool that you either have on the end of your arm or pick up or something. I mean, again, you know, I'm a design guy, so anything that works. Yeah. Yeah.
So,
Yeah.
you know, it's a fascinating idea, but that the tape things,
Yeah.
that can bear load in one particular direction.
Pretty much.
But
yeah.
you know, off the target, you know, and then as you have multiple, you know, cables, multiple of the tape things, you know, I see the kind of situation that creates a kind of awkward force or moment in the standard direction.
Once again, he's completely anticipated the slides that are coming in about 2 more slides. But you're absolutely right. You're absolutely right, and that is absolutely an issue as we start to look at other variants of the design. Yeah. 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 But it's really good because, no, you're absolutely right. It's true. And also these booms, there's a whole science on booms. We have a new faculty member from Caltech, Maria Cutkosky, that's like her thing, is these new space structures. The ones that give you a closed form, of course, are much stiffer in torsion, and they're much better, but they also have more fatigue life problems. So yeah, that's an active area of interest. Yeah. Yeah, good point. Any more questions? Yeah, a couple more.
My guess is the maximum pull force is also dependent on the material of the surface.
Yes.
If it's wet, it's...
Yes. So when we do the limit surface analysis, it's going to be limited by typically one of 3 things. One is that you pull and the spine will just slip because you'll exceed the friction limit at whatever angle that spine is interacting with the surface. Failure number 1. And that's the kind that we actually, if we had to choose, that's the one we want. The second level of spine failure is, and Songbei will remember this stuff from even with Boston Dynamics. The second level type of spine failure is that the spine itself undergoes plastic failure, meaning it becomes more dull, which means it cannot go, it doesn't work on, it only works on rougher materials because the spine tip radius fundamentally is what affects how small a bump or pit can be, and you'll still get stuck on it, right? And the third possibility is that the rock itself fails, which depends on the material. Fortunately, lava rock is actually pretty good. But there are other surfaces, you know, for which the failure of the rock itself, like a sedimentary rock, you know, that's the limiting thing. Yeah.
So you don't pre-consider before you choose a target. You can only figure out if it's fail or not only after you actually try.
We've tried. So based on what we know of the geometry and roughness, assuming the rock doesn't fail, we can predict what the maximum force will be for forces in every direction, right? That's how we build the limit surface. But I don't know a priori whether there's like a crack in that rock that might cause it to fail prematurely. And we've tried actually to do sensing, because you know I do tactile sensing, I love tactile sensing. Could we somehow predict by listening with accelerometers or something like for incipient failure? And it has not been successful. It's about as successful as predicting an earthquake before it happens. Yeah, it's just not been very effective, and that doesn't mean I've totally given up, but it hasn't been successful so far, yeah. And there was another question, yeah, and one more too in the back, sorry.
So you also talked about how this could be used in the lunar environment.
Right.
So one thing that gets me here is, what about the presence of regolith?
Regolith and dust, right.
So how does that affect
Yeah.
the splines and the performance of this gripper?
Yeah, so this gripper you would not use on the lunar surface or on a crater. There's too much regolith and you'd use something else. There are lunar pits with an overhanging surface, and I think this might be fine. We don't know how much dust is on them, based on the angle of repose. There are some lunar pits where there is an overhanging wall, and what's interesting is almost nothing else can explore them, but we don't know how much dirt is on them. A little bit of dirt is not a terrible problem for spines if they can get through it to the rock below. Yeah.
Does it affect the efficacy at all?
Not unless it's so much that it prevents some spines from making contact. Yeah. Yeah. Well, and then, dust mitigation is a whole big issue. How are these booms going to deal as they're in a dusty environment and some dust gets rolled up, which it will. And yeah. And there was a question in the back too before I move on. Yeah.
When you're measuring pull force, are you talking like straight orthogonal out of the wall, or are you talking about?
No, in whatever direction. So remember, I've got a spring-loaded ball joint at the wrist. So I can pull tangentially or normal or whatever.
Are you finding your maximum pull force to change based on the angle?
Yes, that is the limit surface. So when I kind of went fast, but that's an important point. So let me actually go backwards a little bit. When I computed this surface, the reason why the magnitude is different at different angles is just exactly what you were talking about. Yeah. Again, given a 3-fingered, in this case, gripper. Any more questions before I move on? Yeah, sure, go for it.
Can you use the microphone?
Sure.
Do you have any idea about what percentage of a given cave or lava tube is navigable by this gripper?
Yes, I don't have that data with me, but Julia and Stephanie for like at least for the ones in the Mojave Desert, yeah. So a lot of it. Finding good grasp sites was not a problem. There were lots of them. Whether that would be true on the Moon or Mars, we don't know. All right, I'll move on. So you saw us very slowly and painfully targeting sites in the Mojave Desert. I want to talk a little bit now about a little bit of new work. And in particular, one of the things that struck us and also frankly struck NASA is that ReachBot, as we're talking about it here, is a kind of somewhat expensive and complicated looking apparatus. Are there other applications for which you could do something simpler? Okay. What we know from doing, if these beams can only pull, then to ensure stability and force closure, you need n+1 for n degrees of freedom. So therefore you need 7. And if you want to be able to reposition at least one at a time, you need 8. Is this why spiders have 8 legs? I don't know. But 8, that's a lot. But that assumes that the booms only can pull, that really what we get in terms of shoulder torques and the ability to do some compression, especially when the boom's not so long, that we're kind of throwing that away. What's the minimum number of booms you could have? Well, how about 1? It's hard to imagine less than 1, or it's some completely different kind of robot. So we've been sort of looking at that. So here's one where we actually have 2 booms. There's one that you can see in the foreground and one hidden in the back. And the idea is that these booms, what they do is that they will swivel around and latch onto a gripper and then extend with this gripper attached on the end, extend up to a grasp site, let the gripper grip, and then retract but the gripper has a string on it. And now the string is attached to a winch, so I can still apply tension. And so that's the idea of what we're calling RB Light, and we've been doing simulations on it, and already getting some interesting findings. Dan Morton in particular, and Stanley Wang, a new student who's actually from Hannah Stort's lab at Berkeley. So one of the interesting findings of Dan Morton, have any of you been doing grass stuff? How many people here know what the Ferrari-Canny metric is? A few of you, yeah, old timers, I guess, mostly, and a few new timers. Good to see. So it's like the famous grasp theory metric. The gist of it is that you've got a bunch of fingers on an object. Each finger can apply forces subject to friction, so within a friction cone. So if I have a finger and I'm pushing, I can apply a force like this, and then it starts to slip. So I have a friction cone that limits the forces. So if every finger can apply a force vector somewhere, anywhere within its friction cone, you do a convex addition of all these forces, and you come up with a polytope or a polyhedron in force space, and the bigger the better. And one way to do the metric is that you create a circle, a sphere, or better yet, an ellipsoid, which corresponds to the forces and moments associated with the task. And you grow and grow and grow until at some point it intersects your polyhedron, and that's the limit, okay? That's essentially how we do limit surfaces. So here's kind of an interesting result from Dan. The first thing is that when you have booms or cables that are mostly just applying tension, what we call the naive solution is not good at all. The sort of Spider-Man or Leonardo da Vinci Vitruvian Man, the thing's out. It's really bad because why?
Lack of torques.
Torques, yes. It's actually fine for force. The problem is moments. If you want to resist moments, what you need is something that looks like the wheels of your bicycle. You know how the spokes are crossed over so that you can apply torque to the hub and it gets out to the rim? If you had just radial spokes on your bicycle, your wheel would be very soft in torsion. You'd step on the pedal and it would kind of, nothing would happen for a moment until it started rolling. So if you look, next time you go unlock your bike, look at how the spokes are carefully interlaced. And that winds up, of course, being a better solution. And here's the thing. Comparing cables to booms, where the booms have the ability to apply just a little bit of shoulder torque and a little bit of push force that we've limited. The booms, it's not maybe too surprising that booms are really better in terms of robustness. Having the ability to apply a little bit of torque at the shoulder, a little bit of compression really helps in terms of the size of your space. Although if you optimize, it's not that much different. So what we're kind of finding is that as we go to RB Light with maybe just one or two booms, our sensitivity to poorly chosen grasps is getting higher, and so we have to be more careful about that. Any questions on that? This is brand new stuff. I think Dan is sending a paper into IROS on it. Yeah.
So I remember about, 13, 14 years ago, Yoki and Ravi Balasubramanian, they did this paper where they were looking at actually kind of savaging Ferrari-Canny metrics.
Yeah.
But I think there's an interesting sort of nugget in there, which is what they found is that you could come up with these very simple heuristic scores for grasping that correlated much better with success than kind of a wrench volume type metric. And I'm wondering, do you see anything like that for the tension case?
Yeah. Well, so here's the thing. So sort of this classic grasp analysis, what it seems that it's not good enough to reliably give you a good grasp, but it is good enough to reliably throw out a bad grasp. Yeah. So the problem with Ferrari-Canny is that if I'm going to hold this box and I've got some fingers and I want to resist torques, it's going to tell me to do this. And okay, yeah, but how many of us pick up boxes this way? Not so many. And it's actually better, yeah, better than doing this or this. That's less of an issue with ReachBot because we're grasping sites in the world, and the thing that we're grasping, it's our own body, it's ourself with fixed shoulder points. So I don't think some of the issues with finger-based grasping of objects, some of those limitations probably don't apply so much. But it remains to be seen. Yeah, so will eventually there be a machine learning ReachBot solution that's better, by far than what Marco's guys are optimally producing? Yeah, maybe so. Oh, here's another one. Do you suppose there are ReachBot stance synergies? There could well be. Nobody has enough experience with ReachBot to have any idea what they might be, but yeah. Okay, and one more fun thing. So yes, the minimum number is really 1, really lightweight, really low cost. We just used 2 tape measures back to back. This is Stanley's design. I mean, it was great. We were talking about this, and he came in a week later with this whole thing 3D printed. And, by golly, it works. And where we're kind of going with this is to see whether we could get a form factor small enough for some of these. There's a NASA program called CLIPS, which is commercial space operations on the moon. In fact, our latest joke is that the killer app for RB Light is going to be writing toppled commercial space landers, of which there are at least 2 on the moon already. And I have a little bit of a video, I think, of RB Light from Stanley. It's fairly janky, and yet for a week's worth of 3D printing, it's kind of fun. So there it is, hanging itself from a piece of lava rock. There's a very, very simplified 3-fingered spiny gripper. And now our shoulder is brought into the middle of the body with a gimbal mechanism so that it can actually, I didn't explain that. Let me just stop this for a minute. The idea is this. If you move your shoulder axis into the middle of the body and put it on a gimbal, then it can extend, then your one and only boom can extend out any of these square faces. So you can put a gripper here, here, and here, and then you just have to push it, and it has a magnet. So it grabs onto the gripper, goes out and places it, lets go, retracts, and now we can tension the cable to support ourselves, and we can go grip something else. So really minimalist. I think it's more of a thought experiment. I actually think that you would probably want to have at least 2 booms, but it is fun to watch. So like everybody else, it's using Dynamixels and 3D printed parts. And literally these tape measures, 2 of them back to back. And it grabs. It detaches the gripper, but you can barely see it, but there's still a string attached that we can tension. And there it's, okay, yes, in fact, it's hoisting itself up on the string. All right, so I think that is as much as I really wanted to cover today. Let me take more questions. Thank you so much for your time and the questions you've asked already. Yes, please, in the back.
Hi, yeah.
Sorry, I think first and next, second.
So is there a situation where you see the cables being better than the booms?
Are there situations where the cables are better than a boom? Not really. I mean, the booms are really quite strong in tension, and unlike the cables, they're steerable, meaning that I can target a place and go to it. With the cable, I have to get it up there somehow. They're lighter. They're much simpler. I only need a winch. I don't need a pan tilt shoulder and then an extension apparatus. So from that point of view, they're nice because they let your whole package get smaller, more likely that we might get ourselves on a commercial landing program. But from the standpoint of grasping and functional performance, I don't actually think they have any advantages. Yeah.
Awesome presentation on that
thanks.
one. I'm actually sort of got a follow-up to that one and then the original question. On a follow-up to that, I wonder if in like a more dynamic case, could the cables potentially have some benefit? I'm just picturing Tobey Maguire in a moon cave, swinging his way along.
Swinging, yeah. Well, yeah, you can imagine that. I mean, we're nowhere near that. We're moving very slowly. Okay, but from a stability point of view, they're actually worse. And that goes back to that thing I showed from Dan Morton, that if you have a little bit of torsional instability or trying to damp out torsional oscillations, having even a little bit of shoulder torque is really quite helpful. Yeah.
Yeah, and I'm also wondering, I know in some previous work, folks were looking at using for these deployable composite booms for vertical deployments, guy wires to support them. In particular, I'm excited looking at this single deployable case. You've got a cable there anyway.
We
Could
do
that
actually
potentially help?
Yeah, we have more. It turns out we actually have multiple cables because the way it's hard to see in the slide, but at least for that one, I don't know that we're going to do this in the long run. But what Stanley's clever idea is that the gripper is mounted on a little square frame, and there's a cable at each corner of the frame, and they all come together on the same winch. And that means he only has to go with a magnet into the middle of the frame and then start pushing. So could they stabilize the boom a little bit? Maybe. Right now, yeah, I mean, we're certainly not exploiting that at all. Something to think about, yeah. The other point I should make is that the real booms, carbon fiber, are much, much better than these tape measure things. Yeah.
Thank you for a great talk. It almost reminds me of the muscle. Muscle actually extrude out super glue and make a string cut.
Oh, yeah. Okay.
But anyway, the compliance direction, I mean, the climbing error, I built a lot of stuff that we focus on not only normal direction, also tangential compliance. Elliot made us, SMA constant
absolutely.
force. I don't think I saw much.
No, and here's the thing. If you have just a little bit of normal force, positive normal force to work with, then everything is much more forgiving. Actually, climbing a flat wall is very much the worst case. And you and Alan Asbeck, you had to work so hard to make these optimized spine suspensions that had almost no stiffness in the normal direction, because you can't push yourself off the wall, and a certain compliance in the tangential direction such that there's a good probability when one spine grasps that if you pull harder, another spine will find an asperity before you run out of travel. I mean, all that is sort of still true, but it's much less severe because if you have a little bit of normal, and by the way, we're finding this with the gecko adhesive gripping, like at Flexive or other stuff we're doing. If you have a little bit of normal force to work with, life is a lot easier.
Oh, yes,
yeah.
that's true.
Yeah.
Thank you.
Yeah.
By the way, we might be able to find out how to make a tape measure puncture made up feature can zip between them.
Well, Mark Gim has his zipping.
Yeah,
Mark,
even two tape measure.
We have looked already. The one you saw, we're using Velcro. Because we have to, it's hard to explain, but we have to roll them like this, right? Yeah. And then when they come together, they have, I didn't go into the details, but they actually have Velcro down the middle.
Awesome.
So it peels, but they come together. We looked at magnets, they weren't strong enough. Awesome. But actually the best booms, instead of being this way, they're this way, which makes them much, much stronger in torsion, but the problem is fatigue. Because now when you bring it together, well, the good news is you only have to roll it on one side. But the bad news is that the one side undergoes really severe strain. And so we hope that Maria will help us. Yeah, because as soon as we say, but we want to deploy this, this thing that was designed for antenna, but now we want to deploy it thousands of times. Yeah. And actually there's a paper out of MIT where they show boom delamination on structures.
Very cool.
Yeah. Yeah.
So with the cables,
it seems like the consequences of losing a grasp are much higher.
I think so, yes.
Because you can
Yes.
get like tangled and whatever.
I think I agree with you on that. Yep.
So what's the plan?
I'm not sure.
Okay.
I actually think, despite that it was a really clever idea of Stanley, I'm not yet sold on the gripper with 4 cables. Because it's just that much more stuff to get tangled on things. I think 1 cable is not too bad.
Have you considered differentially coupled microspines to improve the load
We
sharing?
do that, yep. When you have, like for perching, where you can only afford to have a very few spines, yes, it's better.
Any more questions? I think there were many questions in the talk, so let's thank our speaker, Mark, once more.
Thank you.
And Mark, we have this chalk for you.
Okay, thanks so much.
Yeah, thank you, everyone, and I hope you enjoy the reception.